So for today's session, we're going to be going over student questions from any of the practice IB exams. I'm going to start by sharing my screen. And sharing the let me try that again. I'm going to share my screen and share the Google Doc. Can somebody tell me if they can see the shared Google Doc?
We can see it.
Yeah, thank you. Okay, it looks a little weird on my screen, so I wasn't sure. Okay, so I see a question in the chat that says, can we see some molarity problems like 2 and 3 on the paper 1 of the grade packet? So I'm guessing you mean from paper 1. Okay, yep, we can definitely do those. We'll start with that. I just want to draw your attention to the spreadsheet where I'm trying to put clues or answers in to supplement what's in the mark scheme, okay? Or to format things in a way to help you understand some of those questions so that if you don't get them answered in class, you can refer to them here or you can look here first. So I am working on doing that for all the questions that are posted, okay? But I got a late start on it today, but I'm getting there. So I'm going to start with I'm going to start with the grade test questions 2 and 3 on paper 1, just because that was requested right now. You can request anything you want, and I'm going to cater to those students that are here in the session. Okay, so we just had a question from the chat. So I'm going to bring up the grade exam, paper 1. And I think it is a problem for students sometimes when you have to do a calculation and you don't have your calculator. And I'm going to maintain that it's not necessarily difficult to do the problems without the calculator. You just have to be comfortable with the setup. Can you see paper 1 on my screen?
Yes.
Okay. So number 2, let's think about this, how to solve these problems. So this is not a molarity problem as such, but it is a moles problem. And so what you're thinking about with a problem like this is the mole diagram or the expanded mole diagram. So we want to know the number of atoms of oxygen in 2 moles of the sodium carbonate. Okay, so think about how can you set this up in a dimensional analysis setup. All right, so 2 moles of the sodium carbonate decahydrate. So I'm going to say 2 moles of that. What do I want to really know about? I want to know about oxygen. I don't want to know about the whole compound. And so when I look at 1 mole of the sodium carbonate decahydrate, how many oxygen atoms are in one of these formula units? So there's 3 there, and there's 10 there, for a total of 13. Okay, so there are 13 moles of O in 1 mole of sodium carbonate decahydrate. Okay, and then finally we want to know, well, how many atoms is that? Okay, we don't want to know about moles of oxygen. 1 mole of oxygen is 6.02 times 10 to the 23rd atoms. So you're probably wondering, right, how to do that without a calculator. You ignore this piece. Okay, so 2 times 13 is 26 times 6. You have to do a little bit of mental math here. $156 times 10 to the 23rd. All right, so in standard scientific notation, that would be 1.56 times 10 to the 25th. And so D is going to be the correct answer to that one. All right, so that involved doing a setup, canceling units. Abira, if you don't mind me asking you, which part of this caused you some trouble?
I think I forgot to add the moles of oxygen.
Yep, and this is a very common question that you'll see, where they'll talk about a certain number of moles in the problem, but then they'll ask you about some subset of atoms in here. And so in this case, they were asking you about the oxygen. So if we have 2 moles of this, we really have 13 moles of oxygen atoms in 1 mole of that. So this factor here is going to become very important in problems like this. Okay. And number 3, also on the gray test, what is the volume in cubic centimeters of the final solution if we have a solution that contains 1.42 grams in, okay. So when it says final, and what to me, this makes me think of that dilution formula, right? Because it says diluted. So we want to know the volume of the final solution. We want to know that. Okay. And the concentration of the final is right there. So we want to end up at 0.020 moles per cubic decimeter. And what are we starting with? Okay, well, we have 100 cubic centimeters. So that is my V1. And what is my molarity? 1. Okay, this one I still need. So I have 1.42 grams. And then if there's 142 grams in 1 mole, you can see that that is 0.01 moles of Na2SO4. And that 0.01 moles is in 0.1 liters or 100 cubic centimeters. So that initial solution is 0.1 molar. And then you would solve for V2. I think this one comes out to 500 when you do that. So that's a lot of math, but that's the amount of thinking you kind of have to do to get through that. That I do find 3 to be a bit of a challenging question on this test. Okay, so let's talk about other questions that you have. So I know that all of these things on the spreadsheet are questions. I don't know who they belong to, so I want to address those of you that are here today. Is there anything on the gray test that you want to talk about?
Can we go over 5?
Number 5 on paper 1?
Yeah.
Okay, and it looks like number 6 on paper 1 is also requested. All right, these are both excellent questions for us to go through in a bit of detail. So be careful on a question. This is first of all an atomic structure question, which is topic 2. They're asking you about the nucleus. How many electrons are in the nucleus of anything? 0. Okay, electrons are not in the nucleus. Okay, then where do we go from there? That's probably where people make a mistake on this one. Now, magnesium, we go to the periodic table. We see that it is atomic number 12. And so that means it has 12 protons, and then it has 26 minus 12, 14 neutrons. So where is that answer? D is going to be our correct answer to that one. So this is very tricky. People try to do this question quickly, and they think if it has 12 protons and no charge, it also has 12 electrons. And that's true for an atom of magnesium. But if we're just considering the nucleus of magnesium, there would be no electrons in there. Okay, number 6 is also a question from atomic structure. Okay, topic 2. Which electron transition emits energy of the longest wavelength? Okay, emit means to give off. So you've got to pick an arrow that's pointing from high to low energy. In other words, B and C represent an electron that's absorbing energy or gaining energy. A and D represent electrons that are emitting energy as they make that transition. Now, the longest wavelength, that means it's a long wavelength means it's a lower energy transition. And so you're looking for the shortest arrow, in which case is going to be A. Okay, because this is the energy difference here. If you measure that, is going to be less than the energy difference here of the longer arrow. Okay, because of the spacing of the energy levels. Any other questions on 5 or 6? All right. Somebody asked about 11. This is another good topic for us to focus on, and it does require a couple steps to answer question 11. All right. And my eraser isn't working for me today. There we go. What are the predicted electron domain geometries around the carbon and the nitrogen? Okay, so we made this distinction yesterday in class about electron domain. That's just about how many positions are around the central atom. It doesn't matter if they're bonded or lone pair. Okay, so in order to answer this question, we need to sketch out a Lewis dot diagram for NH22CO. So we need to count up, and that might be the hardest part of this question. So we have, let's see. You guys recognize the NH2 group. So this is a little bit challenging to do, but CO, you remember from organic, right? The way that the letters appear, the way that the atoms appear tells you about how they're connected. So in other words, these NH2 groups are attached, I'm going to draw it with bonds, are attached to the carbon. So we have NH2, NH2. And then we have to count up all of our electrons and fill in lone pairs everywhere. So nitrogen is 5 times 2 is 10, 11, 12, plus carbon is 16, plus oxygen 6. I think we need to show 22 electrons here, if I've counted correctly. My bonds show me 1, 2, 3, 4, 5, 6, 7, so 14. Okay, so I've used 14, which means I need to put 8 lone pairs in my picture. Okay, do you see how the nitrogens need a lone pair? And I don't think I counted this properly. I'm gonna have to go back and count again. I only have 7. Okay, 14. I think this was supposed to be 24, actually. Did anyone else get 24 when they counted it up? Yeah, it does come out to 24, and this is 10. And so there's our last lone pair. What's the problem with this Lewis dot diagram?
The carbon doesn't have an octet.
What should I do, Sophia?
Make a double bond.
Yeah. So probably the place to do that would be up here, the oxygen. So like not 100% straightforward. Okay, but it doesn't really matter for the purposes of answering this question, okay? But as long as you have the right number of electrons in your picture, you're going to be okay. So looking at that central atom, that carbon, since it has 3 domains, it's going to be trigonal planar. Okay, and then looking at the nitrogens, each nitrogen has 4 domains. You know, 3 of them are bonded, 1 of them is a lone pair. And so the nitrogen are tetrahedral. And so that's the correct answer for this one. So do you think the challenge on that one maybe was not knowing that what the Lewis dot structure was for that compound? Maybe. Okay, what other questions do we have? We don't have to stick to the gray paper. Oh, I will tell you, I'm gonna go over the blue paper 3 tomorrow in class because I want to make sure everyone hears us go through one paper 3 together. Okay, so anything but blue paper 3 I'm up for right now.
Can we go over 22 on paper 1?
On the gray,
Yeah.
22. Oh yeah, this is a very challenging question to think about. I'll tell you what, this question for me was easiest to interpret by a process of elimination, which is what I wrote in the spreadsheet for this one. Let's do it that way to start. Which can describe oxidation? Oxidation is loss of electrons. So let's cross out gain of electrons. What happens when oxidation occurs? So if you lose electrons, your oxidation number actually increases. Okay, so those two answers cannot describe oxidation. Now, another way to think about oxidation is that it could be the gain of oxygen. And so D is also incorrect. So by process of elimination, I'm going to pick loss of hydrogen. There are two definitions for oxidation in chemistry, in IB chemistry especially. One of them is loss of electrons is oxidation. The other one is gaining oxygen. So any questions on that one? And that gaining of oxygen is a very specific and yeah, it's just a very specific definition of the term oxidation. The next question that I'm seeing is number 15 on the same test, I assume, gray 15.
Yeah.
All right. All right, so another one with a mathematical setup. Oh, so that question that we were just talking about is officially redox, which is topic 9. This is topic 5, I believe, which is energetics. Okay, so we're mixing two solutions. The temperature goes up by Y, and then we're given some constants. What is the enthalpy change of neutralization? Okay. So enthalpy change, delta H, is equal to Q over moles of limiting reactant. All right, we know Q is MC delta T. So these are the variables that we're going to want to fill in for our setup to select the correct answer. Okay, so some of these are a little bit easier than others. So we're going to do M. M is the mass that undergoes the temperature change. So we have two 100 milliliter solutions. So that's a total of 200 grams. If we assume that the density of water of this solution is 1 gram per cubic centimeter or 1 gram per milliliter. The specific heat is 4.18. And the delta T was given as Y. Okay, now, how do these look? That one looks wrong, okay? That one's mass is wrong, right? And this one is wrong because when you do delta T, you do not add 273. All right, a change in Kelvin is equal to a change in Celsius. Okay, so that's my numerator. In my denominator, I want moles of limiting reactant. Now I have two solutions. They are equal molar. And so you can use either one as your limiting reactant. So that would be 0.010 moles. Okay, so our units here, when we get through with this, remember 4.18 joules per gram degrees Celsius. That's degrees Celsius. Anyway, you're going to end up with joules as an answer here. Now, joules per mole. But they want us to give the answer in kilojoules per mole. So we have to divide this by 1,000 to get to kilojoules. So then our best answer here is B for that. Okay, so what do we have here? You want to make sure you double the mass. You put the total mass there. And you want to make sure you use only the moles of one of the reactants, the limiting reactant. Okay. Oh, and you also want to make sure that you don't add 273 to an MC delta T problem for a delta T. All right. Anything else?
Could you go over number 1 on paper 2 for the gray?
Just want me to, this might not be a bad one for us to just run through it from top to bottom. Is that what you would like?
Yeah, I kind of was confused on like all of number 1.
Yeah. So what this one does, I'm sorry, there's like a siren going off outside. I can't even think. The IB exam on the paper 2 really breaks problems down into many steps that we would do in one step or in one solution. And so I think that confuses people. Let's try to figure out, I know half the battle on these questions is interpreting the question. What is going on? All right, so try to be careful reading it. That's my first piece of advice. Read everything. A student determines the percent of the active ingredient magnesium hydroxide in a tablet of antacid. Okay, so the tablet is 1.24 grams, but only part of that tablet is magnesium hydroxide, right? So we want to find out the percentage that contains that ingredient. All right, so the tablet was added to sulfuric acid, which was in excess. Okay. Calculate the amount in moles of H2SO4. All right, so part A, the sulfuric acid is 50 cubic centimeters. So all this is, and you don't have to show all these steps, right? But this has to, if we want to know moles and we have molarity, this has to be in cubic decimeters, right? So you have to kind of move the decimal point. And then molarity is our conversion factor. So there's 0.100 moles of sulfuric in 1 cubic decimeter. Okay, now remember, you do have the calculator for this part of the test. And so this comes out to 0.00500 moles of H2SO4. That's all they're asking for in part A. All right, in part B, the H2SO4 from part A is going to react with our active ingredient. What does that reaction look like? So this is just a double displacement reaction. We're going to swap partners here. It's also a neutralization reaction because we get water and magnesium sulfate. All right, and so we would want to balance this. I think we need a 2 right there. And it doesn't hurt to put phases everywhere. Oh, that's a solid tablet. Sorry about that. Okay, so far so good. In part C, the excess sulfuric acid. Oh, okay. So this is weird. This is probably where things break down for you a little bit. So let's think about what's happened already. We put the tablet into sulfuric acid and it reacted. Okay. We know that there was excess sulfuric acid in the container. So question C says, let's figure out how much excess sulfuric acid there was by titrating it with a known volume and concentration of sodium hydroxide. This is basically a titration, right? So now we're going to react whatever H2SO4 was left over from that experiment with this sodium hydroxide. So I'm going to do 0.2080. I'm going to put that in cubic decimeters, 0.02080 cubic decimeters times 0.1133 moles of NaOH per cubic decimeter. And then I do a mole ratio. So moles of NaOH to moles of H2SO4. And that will tell me how many moles of excess acid I have present. Now, before you fill that mole ratio in, you need a balanced chemical equation. NaOH plus H2SO4 yields H2O plus Na2SO4. Balance it up to there. And you'll realize that you need 2 moles of NaOH per 1 mole of H2SO4. So you do the math and you find out that 0.001178 moles of H2SO4 were left over by this reaction. So in A and B, we reacted the tablet with the H2SO4. In C, we took the extra H2SO4 and reacted it with sodium hydroxide. So then in D, how much H2SO4 originally reacted with the magnesium hydroxide? So you take your answer from part A. I originally had 0.00500 moles of H2SO4. At the end of all of this, I had excess H2SO4 present. How much reacted? And this is just that subtraction problem. So we've done these problem types before. This is excess. We haven't really formatted them this way or done it in such a stepwise fashion. Do you want me to keep going with this problem? Does anyone need to see parts E and F? Okay. When you are doing the first part of a question and you are confused or you make a mistake, just do your best to come up with a meaningful answer that you can carry on to the next part, okay? There's always error carried forward. All right, so here we are at part D, and I have what is the correct answer up there, but maybe you don't have the correct answer. Pretend you do, okay? Go on to part E with the information that you calculated. Don't give up, even if you feel frustrated or confused, because whatever answer you used can be carried forward correctly in the next part. Let's try that. Determine the mass of magnesium hydroxide in the antacid tablet. Okay, So, well, we never figured out the mass of magnesium hydroxide or the moles of magnesium hydroxide. The only thing we do know is that we had 0.00382 moles of H2SO4 that reacted. Okay, so using our balanced chemical equation, for every 1 mole of H2SO4 that reacts, we react 1 mole MgOH2. Okay, that was our reaction that we wrote in part B. And if I know moles of magnesium hydroxide, I can use the molar mass to calculate grams of magnesium hydroxide. So again, if you made mistakes in parts A through D, whatever number you came up with, you can bring it down right here and get part E correct. Okay, if you set it up correctly. And then percent by mass is equal to the part over the whole times 100, right? Like you would do a percent composition. So we have in part E 0.0223 grams of magnesium hydroxide. The whole tablet was 1.24 grams. What percentage is magnesium hydroxide? And this comes out to about 18, it looks like. Okay. So this is going to happen, especially on problem paper 2, question 1. Usually there's one question that's going to involve stoichiometry. And this whole question is about stoichiometry. Now, I know that's frustrating to go through, but you have 5 tests. Each of them will have an example like this. So you're going to get more practice. All right. Let's do a couple more questions before we wrap up for today, okay? What else would you like to go over?
Can we go over 3CI and 3CI2?
Same test?
Yeah.
Yeah. Oh, this is a great one to discuss. Hopefully I'll put your mind at rest a little bit after I talk to you about it. 3C1 and 2. Okay. So they start this whole question this whole question has something to do with copper, it looks like. Oh no, just this part of the question has to do with copper. Okay, so we have these little boxes presented to us. This is where you would draw the electron configuration. It's an orbital diagram. You would look copper up on the periodic table. You would see that it has 29 electrons. You can also look up its position on the periodic table. So it's in the D block. And so you want to figure out how many valence electrons it has. So we look at its position in the periodic table, and we see that it has, let's see, 9, I think it has 11 valence electrons. Okay, there's 4s2 fills first, and then 3d9, you might think, right? So this is probably what most of you drew for question C1. Okay, so I always say look at its position on the periodic table and then fill in its configuration. Now, unfortunately, copper is an exception to the electron configuration rules. Instead of filling the 4s first, it sort of combines these energy levels as being very close to each other. And one of these 4s electrons actually gets paired up over here so that we have a totally filled sublevel of 10 electrons. So I want you to make a note on your test that this is an exception and it will not be tested on your final. Okay? Surya, was that your question about 3I, 3CI?
Yeah.
Okay, the fact that was an exception, right?
Yeah.
Okay, now part 2 of this question is an electrolysis. Okay, so electrolysis is when you add energy to make a chemical reaction occur. So they're describing how the cell is set up. And so we have metal, we have copper at the anode, and anode is where oxidation occurs. And that's the impure copper. And then over at the cathode, we have, that's where our pure copper is going to be formed. Okay, so cathode, what happens at the cathode? Reduction. And then the electrolyte that we have is copper 2 sulfate. So what you want to think about to yourself, what chemicals do I have available here? I have copper, I have copper ions, and I have sulfate ions. So when you look at those combinations, you can figure out that there's not very many options here of what processes are occurring. So since oxidation happens at the anode, let's write this as an oxidation, a loss of electrons. So these two are interconverted. What happens at the cathode? Something has to be reduced. Copper 2 plus is going to gain electrons to become copper. All right, so that looks weird, right? Because you're doing the opposite process at the 2 different electrodes. So think about it like this. The anode, which is impure, is going into solution as copper ions. And those copper ions are coming out of solution at the cathode to make pure copper. That's what's happening in this process. And the sulfate, just a spectator in there to allow electricity to flow through the solution. Okay. 3A, part 2. Okay, this will be the last one we have time for today. So keep asking questions. This has been helpful. Okay, 3A2. All right, so draw the first 4 energy levels of a hydrogen atom and label them. Okay, so be careful on this. What they want you to do, I know you didn't ask about this part, so I have to just go backwards a little bit. N equals 1 is our lowest, then N equals 2, and then N equals 3. And you want these lines, remember when I said you get higher energy levels at greater distance from the nucleus? The energy levels converge. That means they get closer together. Okay, so you want to draw a diagram, something like that. Draw the lines on the diagram that represent the electron transitions to N equals 2 in the emission spectrum. I guess there's no other way for me to say this other than this has to be memorized. Okay, so find it in your IB review book. And you've got to memorize this for the emission spectrum of a hydrogen atom. There are 4 lines. We talked a little bit about this in class the other day. There's a violet, a blue, a teal, and a red. Okay, so let's think about that. We don't have to talk about colors for this one, but violet, and all of these transitions are the result of electrons going down to energy level 2, okay? So how do you go down to energy level 2? You had to either start at energy level 3 or energy level 4. If we had more energy levels available to us, I'm going to just sketch these in. It's not part of this question. Let's say this is N equals 5. All right, and N equals 6. we would have more transitions. We could go from 5 to 2, and we could go from 6 to 2. Do you see how the length of those lines are changing? Okay, so the greater the difference in energy level, the more energy is given off. Okay, so N6 to N2 is going to be our violet line. N5 to 2 is going to be a little bit lower in energy. That's going to be our blue line. 4 to 2, a little bit lower in energy, gives us our teal or greenish blue line. And 3 to 2 gives us our red line. It's the shortest transition shown on the diagram, so it corresponds to the least amount of energy. How's everyone doing?
I have a question. How come there's no transitions from 1 to 2?
That's a great question. There are transitions from 1 to 2. However, the amount of energy involved in those transitions is not viewable in the visible spectrum. Okay, so say you had a transition that went from 2 to 1. Okay, now my diagram is not to any particular scale. Okay, 2 to 1 can happen. It's an allowed transition, but it gives off so much energy on the electromagnetic spectrum, we're outside the visible range. Now we're probably a UV light being given off. Okay, so it wouldn't be detected in the hydrogen emission spectrum because the hydrogen emission spectrum is only showing you the visible light transmissions. Does that answer, Sophia?
Oh yeah, so it wouldn't be correct because it said the electron transitions in the emission spectrum.
What's that? Can you repeat it? I'm sorry.
So it wouldn't be correct for this problem because it says specifically in the emission spectrum.
Yeah, and it, oh, so you're saying, could you have drawn one that goes from 1 to 2?
Yeah.
Okay, so 1 to 2 would be part of an absorption spectrum, not an emission. So on that account, it's incorrect, okay? Because that would be an absorption of energy. But also, like I said earlier, that amount of energy that's being absorbed is outside of the visible range too. So we wouldn't, even if we're going the other direction, we wouldn't expect to see anything in the spectrum. Yeah, I'm sorry if I confused things a little bit there. The reason why you wouldn't draw anything from 1 to 2 is because that would be an absorption instead of an emission. Is that okay?
Yeah, that clears it up.
Okay. All right. Well, that's probably all we really have time for today. Believe it or not, I have one more meeting before my day ends. So keep working on these tests. Tomorrow we have a double period. I will continue to update some things in the spreadsheet. If you want to type a direct message to me before you go about anything, if you found this helpful, if there's anything more I can do to be helpful, and if you like the spreadsheet or not, just to give me a little bit of feedback. I won't take it personally if you don't like it. But I'm going to say goodbye for today. Thanks for everything. I'll stay on just in case people have a second to put something in the chat. Have a great day, everyone.
Thank you. Have a nice day.
Understand.
You too. Bye-bye.